Okay, my name is Rúnar. I'm going to be talking to you about adjunctions, which is an idea from category theory, which is what we really talk about when we talk about monads. This talk is very conceptual, so there's no practical stuff in here at all. It's all just totally for fun and just something to think about in your work and in your everyday life. All right, so I am a lead engineer at a company called Tact. I do Haskell full-time, and we are doing cool stuff with machine learning and Haskell and Scala and purely functional programming. And so if you want to work with me, contact me. I'm Rúnar at tact.com. I also wrote this book with my friend Paul. It's called Functional Programming in Scala, sometimes affectionately known as the Red Book. And it's really great. Thank you. So if you haven't checked that out, you should. OK, so here's the plan. I'm going to teach you category theory, step 1. And it's going to go kind of fast, so be alert and try to keep up. I'm going to show you this pattern of adjunctions over and over again. And I'm just going to say adjunction a bunch. And then you're going to start seeing adjunctions everywhere in your everyday life and in your work. And then you're going to tweet and blog and tell me about all the cool adjunctions that you see in your work. Cool. So that sounds like a plan. OK, so first, let's talk about categories. So adjunctions arise in the setting of category theory. So I'm going to teach you all category theory right now. All right, so when we have functions, so this is sort of Haskell syntax. When we have a function f and a function g, the function f goes from the type A to the type B. That is, it takes an A and returns a B. And then the function g takes a B and returns a C. Every time we have two functions like that sort of match on the output of one and the input of the other, we can compose them. We can compose them into composite functions g compose f. There's g after f, and the implementation is just lambda of x, g of f of x. So we can compose functions. Great. As long as the types match up. And composition is associative. That is, if we have three functions, f, g, and h, it doesn't matter if we consider, and we want to compose them into the composite functions h compose g compose f. It doesn't matter if we compose f with h compose g, or if we compose h with g compose f. All right, it's all just the one composite function, f compose g compose h. Actually, h compose g compose f, sorry. So it's h after g after f. Great, and that, so all of the arrows, all of the routes or the paths through this diagram are the same function. And we say that this diagram commutes. That is, all the paths through it are the same. They're a function from A to D. Great. So for every type A, we also have an identity function that goes from A to A and sort of does nothing, in the sense that if we have another function f that goes from A to B, composing that with the identity function is just f. And composing on either side does nothing, right? So in general, a category is some objects, and so it could be anything. And then there are some arrows between the objects. So an arrow has a start object and an end object. And then there's some composition of arrows, which is associative and has an identity. And that's category theory. This is all of category theory on one slide, right here. So the category that we just looked at, which is the category Hask, the category of Haskell types and Haskell functions. And the objects in that category are the Haskell types. The arrows between the objects are Haskell functions. They have a source type and a destination type, right? So they're directed arrows. And composition is ordinary function composition, which is associative because the implementation of f compose g compose h is lambda of x, f of g of h of x. And the identity is lambda of x goes to x, right? So the identity function. All right, so that's the category of Haskell types. All right, so now let's go back to adjunctions. So what are adjunctions? Saunders Mac Lane famously said that adjoint functors arise everywhere. And the Wikipedia definition of adjunctions gives us this cool definition that an adjoint functor is a way of giving the most efficient solution to some problem via a method which is formulaic. Right? So it finds some really efficient solution, or the most efficient solution to some problem via a formula. And when you hear formula here, you should be thinking functor. Right? So it finds a functor that solves some problem. And if we reason about that sort of the other way, we should be able to find the most difficult problem that a particular functor or formula can solve. Cool. So that's sort of like why adjunctions are cool. But I'm not quite going to just like come out and tell you what they are. I'm just going to give you an example. So an example is one that involves curried and uncurried functions. Right? So what we have is an isomorphism. That is, we have a one-to-one mapping between curried and uncurried functions. So curry takes a function that takes a pair. So that function takes a pair of a and b and returns a c. And we can curry that to turn that into a function that takes an a and returns a function that takes a b and returns a c. Right? So we can partially apply the curried function. And then uncurry goes the other way. We can take this sort of curried function that can be partially applied, and we turn that into a function that returns a pair. That takes a pair and returns a c. Right? So the implementation is pretty straightforward. And if you're not familiar with Haskell syntax, then the thing to note here is that space is function application. So fab means send the arguments a and b to the function f. Right? So just imagine that there are invisible parentheses there and a comma in between if you're used to Scala. OK. So curry and uncurry really witness an isomorphism, or a one-to-one mapping between these two types. So a comma b to c and a to b to c. Like these two types are the same. That is, they're isomorphic. There's a function that goes one way and a function that goes the other way. And so there's one of each. There's one in one of them exactly when there's one in the other. Right? So there's a one-to-one mapping here. And really what's going on here, I want to say, is that this is a relationship between two functors. And the functors involved are pair with b and function from b. OK? So here I'm saying that there's a one-to-one mapping between the arrows, or the function types, f of a to c and a to g of c. Right? So when I have one on one side, I have exactly one on the other side. Right? And so I'm going to have some kind of isomorphism that witnesses that one-to-one mapping. So whenever we have this kind of relationship, we have an adjunction. Right? And so we can talk about adjunctions in Haskell by just using a type class. So this is just sort of a bit of Haskell here. So type class is sort of like an implicit in Scala. So we have this class, adjunction, that takes two functors, f and g. So these are type constructors, f and g. And we say that there's an adjunction between f and g when we have a witness to this isomorphism on these types. That is, the left adjunct will take an f of a to b and turn it into an a to g of b, and the right adjunct will go the other way. Right? So this is the one-to-one mapping. So we just have one function that goes one way and another function that goes the other way. Okay? And then there's a law of adjunctions that says that if you go left and then right, that's the identity. Right? So it's an isomorphism. And if you go right and then left, that's also the identity. Right? Great. So we can have an instance of adjunction using curry and uncurry. So curry and uncurry now witness this isomorphism that is our adjunction between pair with s and function from s. And to go back to the sort of the Wikipedia motivation, you'll note that the pair with s is sort of an optimal solution to the question posed by a function that takes an s. All right? So pair with s is like a producer of s's, and then function from s is like a consumer of s's, and the producer and the consumers are matched exactly. Right? And so conversely, function from s is like the most difficult problem that you can solve using an s. Right? Anyway, and so this adjunction is witnessed by curry and uncurry. So there are some other things that fall out of this. So whenever we have an adjunction like this, we also have a unit and a co-unit. And the unit goes from the type A to the type G of f of A. So now we have a composite functor, gf, and we can go into that functor. Right? So this turns out to be a unit or a return or a pure for a monad gf. All right? And that is just taking the identity function across the adjunction. So what corresponds to the identity function is going to be this unit. And on the other side, what corresponds to the identity function is going to be a co-unit for a comonad fg. So it's going to take you from f of g of a to a. So we're going to see that more concretely now. I just want to say that these can be defined in terms of each other. That is, if you want to define an adjunction, you have to define either the left adjunct and the right adjunct that witness the isomorphism, or you have to give the unit and the co-unit, and they can be defined in terms of each other. Okay? So the minimal definition is sort of like a combination of the unit and the right adjunct, or the co-unit and the left adjunct, or the unit and the co-unit, right? So 2 of these you have to give. Great. So in general, we say that f is left adjoint to g when we have a situation like this in 2 categories. So given a category C and a category D, if we have an arrow in C that goes from f of z to x, we're going to have exactly one arrow in D that goes from z to g of x. All right, so this is the sort of isomorphism on the arrows. And in our example with the curried and uncurried functions, what's going on here is the isomorphism between curried and uncurried functions. Right? And both of the categories here are Haskell, the category of Haskell types and Haskell functions. Okay? And the 2 functors involved are pair with s and function from s. And we say that the pair with s is left adjoint to function from s. So there's another interesting thing that's going on here, is that if you start with x in the category C, and then you go g into D, you get to g of x. But then if you go back into C using f, you don't get back to x. You get to f of g of x. So it's not the same place where you started, but there is an arrow out of where you started to where you, out of where you ended up into where you started, right? So, and that's the co-unit. And that corresponds to the identity function, in the isomorphism. And conversely, on the other side, if you start with z and you go f, you get f of z, and then you go g, you get to somewhere that has an arrow into it from where you started. Right, so it's not sort of an exact inverse. It's kind of like an adjunction is kind of like an approximate inverse in some sense. Okay? So that's just something to think about. So in our particular example of curried and uncurried functions, both of these categories are Haskell. And here, the isomorphism here is, so if we have the identity on the type s to b, right, so it takes a function from s to b and returns that same function. If we take that across our adjunction by uncurrying it, then we get a function from a pair, which takes a function s to b, which is a function from s to b, and an s. And if we take that s and give it to that function, we get a b, right? So we get a sort of a co-unit, whatever that means. And that turns out to be a co-unit for a comonad that I'm going to talk about. And then on the other side, if we have the identity on pairs, a comma s, so it's going to take an a and an s, and it's going to return the same a and s, and we curry that identity function, we're going to get a unit, which is going to take an a, and it's going to return a function that takes an s, and it's going to return that a together with that s. Right? It's pretty simple. But, I mean, the implementation is obvious, sort of. So what this actually is, if you are familiar with a state monad, this is the unit for the state monad, right? So it models a Mealy machine. So the A is the input to the machine, so the input S is the input state, and then the pair A and S is the output state together with the output of the machine. And so this is going to be a sort of a state machine that does nothing interesting with its state. So it's the sort of the unit state machine. Right? So, and we can just write that in Haskell as a state SA. But what's interesting that on the other side, we also get a comonad. So we get the state monad out of this, but we also get a store comonad. And I'm going to talk about what that is here in a bit. OK, so a little refresher on the state monad. So the type state SA is really just a function. So it models the state machine. So the input S is the state before the machine runs. The output S is the state after the machine runs. And the A in the output is the output of the machine. All right. If we compose these functors, so pair with S and function from S, if we compose them the other way, we get a comonad called store. And that, we can see that as a store full of A's indexed by S. That is, for every S, we can get an A. And we have a sort of a current S. And we can ask, what is the current A? Just by passing that S to the function. And we can also change what that S is. Like we can assign it to a different S and then ask, what's the A under that, right? So it's kind of like you can imagine it as like a forklift where the position of the forklift is the S. And then we can ask, OK, what's the A right here? And then get it. Yeah? For example, you can imagine a store indexed by pairs of integers containing colors as being a two-dimensional bitmap. Right? So if we just sort of turn the crank on our adjunction, if we take our co-unit for the store comonad and we map it, that is, across the function from S functor, we end up getting a join for our state monad. And I sort of annotated that to see like how that interacts. So it takes a nested state machine and turns it into a regular state machine. And the way that works is that it will run the outer machine, take the output state of the outer machine, pass it as the input state to the inner machine, and then it will return a state machine that does both of those things. Right? So it's a sort of a composition of state machines. So that's the join in the state monad. And the implementation is just fmap counit. And remember that counit was just, what was it, Curry identity. Great. So, right. So what's a monad? All right. So a monad takes it's two things. So it's a functor together with these two methods. So you have this return, something's called pure or unit, and that takes an A and turns it into an M of A, right? And so that's going to be our unit that comes out of our adjunction. And then we get a join, which we just saw, and that takes nested M. So for our monad M, takes an M of A and turns it into an M of A. So a state machine full of that returns a state machine and turns it into a single state machine, right? Or a list of lists and concatenate all the lists or whatever. And usually that's written in Haskell using return and bind. And so this greater than equal thing is read bind. In Scala, it's usually called flat map. And that's implementable in terms of unit, fmap, and join. OK, so not only do we get a join for our state monad, we also get a duplicate for a store comonad, which is kind of cool. So if we start with a store, we can get a store full of stores. And the way that's sort of going to work is that at each index of the store, we're going to have, sort of at each location in the store, we're going to have another store that has the current sort of index is it's like that location in the store. And I sort of annotated that as well. And you can view the nested store as a state machine together with sort of an input state. And that state machine returns functions that take S's and return A's. So basically, you have like a state machine that models all of the states of your forklift. Anyway, that's super cool. But why is that useful? We're going to get to that in a minute. So first, what is a comonad? Well, so it's sort of the inverse of a monad. So instead of having a return or a unit, we have a co-unit or an extract. That is, if we have a W of A, where W is our comonad, we can go from W of A to A. Like we can extract our A out. And instead of having a join, we have a duplicate. That is, we can add a layer of W's instead of collapsing two layers of W's, right? And just like where we defined a monad in terms of return and bind, usually we define comonads in terms of extract and cobind, which is that equal greater than thing. And that's sort of the dual of the flat map operator. So, and that's implementable in terms of fmap and duplicate. OK, great. So why is a comonad useful? Well, so it extends a local computation to a global one. So for instance, let's go back to our two-dimensional bitmap. So you have a store full of integers, and think of those integers as grayscale values. And then the pair type is going to be our x and y coordinates into that bitmap. Okay, so this is sort of an int-sized bitmap. And so if we know how to take the mean of, so we have a particular pixel that we're looking at, so sort of the index into our store. If we know how to take the mean of all of the surrounding pixels around that particular pixel, we can extend that local computation to a global one to get a low-pass filter over the whole image. And we just get that kind of for free in the store comonad. And if we sort of do this exercise again, if we take the difference of the low-pass filter and the identity, and we extend that over the whole image, we get an edge detector, which is kind of cool, because what we started with is just an isomorphism between curried and uncurried functions. But like, you know, we can do all kinds of cool stuff with just identity, curry, and uncurry, right? OK, so that's one example of an adjunction. Let's go to a totally different example. Like I said, I was just going to show you a bunch of examples. All right, so let's go to the category of integers. So this category is not at all like the Haskell category. The arrows here are not functions. The arrows and the objects are not types. The whole category is the category of integers. So every object in this category is an integer. And there's an arrow from the integer a to the integer b exactly when a is less than or equal to b. And then there's a composite arrow. So if a is less than or equal to b and b is less than or equal to c, there's a composite arrow from a to c because a is then less than or equal to c, right? So arrows composed by the sort of the transitivity property. And then there's an identity arrow on every object, on every integer a. And that identity arrow is just the fact that every integer is less than or equal to itself. Okay, so that's the category of integers. And composition of arrows is associative. That is, it doesn't matter which path we take through this diagram. It commutes. That is, it amounts to the fact that a is less than or equal to d. OK, so an example of an adjunction in this category is between multiplication and division. And so this is multiplication and division on the integers. So given three integers, x, y, and z, where y is greater than 0, we say that there's this isomorphism, or that z times y is less than or equal to x exactly when z is less than or equal to x divided by y. Okay, so that's sort of a specification of what integer division actually is. So it's going to be some, so x divided by y is going to be some value which is greater than every z, which when multiplied by y is less than or equal to x. Okay? All right, so we have a unit and a co-unit. Right? So if we say x and then divide by y and then multiply by y again, we get to somewhere that's less than or equal to x. That is, we may have had some remainder, and when we divided, we lost that remainder, and so we go below where we started. Right? So going across the adjunction and back doesn't get us exactly where we started, but somewhere where there's an arrow into where we started. So that's our unit. And the co-unit is the fact that if we multiply by y and divide by y again, we go somewhere above where we started. Cool. So that's an adjunction in the category of integers. And in general, when we have on this sort of partial order, an adjunction on a partial order like this, that's called a Galois connection. And really what's going on here is that this is a relationship between functions. So the functions f and g, where f is multiplied by y and g is divided by y. So it's a relationship between those functions. But those functions are really functors. They're functors in this category of integers. Great. Let's take another one. So conceptualization as an adjunction. This is one sort of from in everyday life. And it's another example of a Galois connection. OK, so consider all the stuff in this room. And so we're going to say that there's a category of all the things in this room. That is, we can take a collection of objects in the room and call that, a collection of things in the room and call that an object in our category. For instance, like those two chairs over there, that's an object in our category. And like that column and the carpet, that's an object in our category. And we're going to say that there's an arrow between collection 1 and collection 2 when collection 2 contains all of collection 1. So this is an order. And then we're going to have another category, which is our descriptions of those collections. And that's going to be sort of sets of attributes. For instance, like the carpet, it has the attribute that it's gray. And the chairs have the attribute that they're white and that they're chair-like or something. And so the descriptions are going to have this relationship that the description D1 is below D2, or it has an arrow into D2, exactly when D1 is more specific than D2. That is, when it has more attributes. OK. So then I'm going to have two functions, or functors. So I'm going to have a functor going from the objects to the descriptions, and I'm going to call that describe. And I'm going to have a functor going from the descriptions to the examples, or the objects, and I'm going to call that examples. And I'm going to say that these need to be an adjunction. So what I'm saying is that my specification for conceptualization is that when I start with some set of objects and I say describe, that describe thing should be left adjoint to something that gives me all the examples of that description. Right, so if I say, give me all the examples of the description D, and then I say describe all those examples, I should get something that is more specific. I should get a smaller object than I should get a description that is more specific than the one I started with, right? Because, let's say I start with, I don't know, thing, or like person or something. And I say, well, give me all the examples of a person. And then I say, well, describe. And I may end up with more specific, because like all the people in here might be software engineers. And so I end up with the description software engineer, which is strictly more specific than describe, right? Something like that. And so then and the other way, when I say, well, describe this example, and then I say, give me all the examples, I should end up with like a bigger thing. Because like if I take, one person, and I say, describe this person, and I get person, and I say, well, give me all the examples of person, and I get all the people, right? So I've lost so it's not an exact inverse. It's an adjunction. So describe is left adjoint to examples here. And it's a relationship between these two functors in this way. So yeah, let's take I'm going to just fly through this real quick. So let's solve a simple API design problem using an injunction. OK, so let's say we want to write this index of thing that takes an A and a list of A, and we want to find that A in our list. So there's a problem because this should return an integer, and the element may not exist in the list, right? So we have an equality on A. We want to compare, that A with an element in the list, and we want to find it. But that may not work. So what do we return? Well, we can return -1. We can return infinity, negative infinity, not a number, or null. And all of these are things that people have done in the past in APIs. And it's horrible. So what do we want to do instead? So what we actually want is for our return type to have sort of like a special value. So we want to say that our return type should be a pointed type. That is, it should have a specific point in it that is special. And so I'm just going to say there's a class of pointed types where the point is a particular A for a given pointed type A. OK, so the question is, can we turn any type into a pointed type in a universal way that is systematic and works for every type, making no ad hoc choices? And it works out that there's a functor which forgets that a type is pointed, in case you do the pointed types, from the pointed types to the regular types, and forgets the point. It gives you just the underlying type. For instance, if you have the integers with a point like -1, you can just forget that -1 is the point, and now you just have the integers. It turns out that this thing has a left adjoint that takes you from the types to the pointed types, such that for any type x, p of x, where p is this functor, which will find us a free pointed type for any type. And that's going to be an adjunction like this. That is, it's going to be an isomorphism on these arrows. So p finds our free pointed type. So the blue stuff is the pointed types, and the red stuff is the regular types. But the forgetful functor thing just forgets that b is a point. And so we're just going to sort of simplify that into this. So it's going to be an isomorphism on these types. So turn the crank on the adjunction, and we just get, well, we need a right adjunct that looks like this, and we need a left adjunct that looks like that. And so we get a co-unit and a unit. And so for any pointed type B, if we have a P of B, we get a B, et cetera. And so we should get a unit for a monad, and we should get a co-unit for a co-monad in the category of pointed types. And if we just sort of flip these things around and look at this right adjunct, that should look familiar to people who have worked with maybe or option, because this is actually turns out to be isomorphic to option. And so this type this free pointed type will just have this method on it that folds the option, and that's our right adjoint. So it's going to be this function here. So it's going to take a maybe A, it's going to take a sort of a default B, it's going to take a function that turns the A into a B and returns the B, right? So this is sort of fold on options or on maybes. Great. And we get a join for a maybe monad, and we get a duplicate for a maybe comonad in the category of pointed types. And so what we really want is for index of to return a maybe integer or an option integer. And so this idea of option or maybe falls out of adjunctions like this. And we can do this for monoids as well. Like, oh, can we turn any type into a monoid? Yeah, we can. So a monoid, has an append. Like you can take two A's and put them together, and it has an empty A for some notion of empty, which means that if you append the empty to anything, that's just that same thing. So can we turn any type into a monoid? Yes, we can. We just have a forgetful functor from the monoids to the regular types. And that turns out to have a left adjoint that gives us a free monoid for any type X. And we just turn the crank on the adjunction and see what we get. And so what we get is something like this here. And that should look kind of familiar. That is full map. So for any monoid M, if I can go from A to M, then I can go from T of A to M for any foldable T. Great, so the canonical example of that is list. So my free monoid is really just list. So lists fall out of this as well. We can do this again. Can we turn a functor into a monad? Yes. OK, so there's a free functor that takes a functor to a monad. And it's going to be a left adjoint to a forgetful functor that takes a monad to its underlying functor. Right? So for any functor f, free of f is going to be a monad. All right, so we just fill in the types in the adjunction and see what we get. So we're going to get this thing here. We're going to get a co-unit for a comonad in the category of monads. And that is going to go, if we have a free of M of A for some monad, we're going to be able to fold that free into an M of A. So given that there's a monad. And we're going to have a unit for our free monad as well. And if we just keep turning the crank, we get a join for our free monad. And we get a duplicate for a comonad, which is it's going to be a comonad in the category of monads. Cool. So free in general is left adjoint to forgetful functors. And we're going to have also, sometimes we're going to have right adjoints to forgetful functors, and those are going to be co-free. So we can get co-free comonads this way as well. So just as a last thing, adjunctions compose. So if you have F left adjoint to G and P left adjoint to Q, FP is left adjoint to GQ, which is really cool because in general, if you know one half of an adjunction, you can find the other one. So if you know any two of FP, G, and Q, you can find the other two. And this is used in these awesome papers that I'm just going to flash up here. Generic Programming with Adjunctions by Ralph Hinze and Calculator, functional prototype of a Galois Connection-based proof assistant. These are awesome papers, and they talk about how to do generic programming using adjunctions. OK, don't really have time to go into these sort of philosophical things of adjunctions, but come talk to me afterwards if you want to talk about adjunctions some more. So whenever we're looking for a general and natural and elegant solution to some problem, just express the problem as a functor and find its adjoint. It's as simple as that. So adjoint functors are everywhere, and we should totally go look for them. Thank you.